Hi everyone, and welcome to the second tutorial of the Valorant series. Today we are going to recreate the KO Fragment grenade material in Unreal Engine 5. To get started, let's have a look at the effect we want to replicate. Here's a video recorded inside of Valorant, where KO holds the grenade. We can see it's a geodesic polyhedron, or simply put, a sphere made by triangles. The triangles are not flat, they have some thickness, and each of them is moving separately. The coloring follows a purple to light blue gradient going from bottom to top, while the sides of the triangles are white. We are going to replicate all of that from start to finish, so let's go. First of all, we need a mesh for our grenade. The shape looks complex, but it can be easily generated inside Blender using an icosphere. Open Blender and delete everything in the scene. Now press Shift A and select Mesh Icosphere. In the icosphere settings, increase the subdivisions to 3 to have more triangles. Be sure to have Generate UVs option checked. Okay, our base shape is in place. Now we need to separate all the triangles on the surface. So let's go in Edit mode by pressing Tab. Go in Face Select mode and all faces should be selected. If not, just press A to select all of them. Select Inset Faces, then pull the yellow ring. If nothing happens, it's normal. We just want to make Blender show the Inset Options panel. In that panel, check the individual option. Now, if you increase the thickness of the inset, you'll see it happen. I went for something like 0.011, but you can choose the value you prefer. Let's uncheck the Offset Even option to avoid two big gaps where 6 triangles meet. Now, be sure to keep this selection active. Right-click and select Separate Selection. You'll see another icosphere appearing in the scene collection, and that's the one we need. So exit Edit mode by pressing Tab and delete the mesh not needed. Okay, let's give these triangles some thickness. We'll have to extrude the faces, but it's important to do so along their normals that are orthogonal to the faces, in order to keep a spherical shape. So select the mesh and go in Edit mode. Be sure to be in Face Selection and press A to select all of them. Then right-click and select Extrude Faces along normals. Move the mouse a little and left-click to make Blender show the Extrude panel. Here we can fine-tune the offset. I went for 0.04, and be sure to have all the options not checked. Fine, our geometry is ready, but we are not done in Blender yet because we need to set up its UVs. Move your mouse to the upper edge of the screen, just a little left of the editor type icon, and left-click without releasing and drag to the right to create a second view. Here, set the editor type to UV Editor to show the UVs of our mesh. Select the UV Sync Selection option in the upper left section of the window. If you see the editor empty, it's because you are in object mode, so be sure to have your mesh selected and to be in edit mode. The UV viewport is already populated because when created the icosphere, we checked the Generate UVs option. Zooming in, we can see that each triangle has its own UV island. In fact, selecting one face in the 3D viewport, the corresponding UV will be selected in the UV viewport. Now, what we have to do is to reduce each island to a single point. And the reason why we need to do it is because in Unreal we will use the Vertex Shader to make the triangles move. But I will explain it better later in the video. To scale down the UV island, we have to be in Face Selection mode in the UV viewport, and select one face and press L to select all linked faces. Then we can scale them by pressing S followed by 0 to collapse all the faces to one single point. Then press Enter to confirm. We have to do this for all the UV island, and yes, this is a pretty tedious process, but it's necessary. If you want to skip all of that and you want to support the channel, I've made the FBX file available on Gumroad for a small price. Check out the link in the description of this video. Of course, the file is also available for the Patreon supporters. Okay, so here's how the final UVs looks like. we have the right geometry and the right UVs, so our mesh is now complete and ready to be exported. To export it, go to File, Export, and select FBX. Here we can leave everything as it is, except for one option. Under Geometry, set the smoothing to Face. Finally, click on Export FBX and close Blender. Fine, now it's time to fire up Unreal Engine and import our FBX by dragging it inside the content browser. You can leave all the settings as they are and click Import. Then place the mesh in your map. Let's now create our material and give it a meaningful name. I've called it M_KO grenade and then open it. We are going to start from the color. We want a gradient that goes from purple to light blue. So let's create two constant vector tree by holding 3 on the keyboard and left clicking in an empty zone. Let's convert them to parameters, so later we can use a material instance to control them without having to reapply the material. I've called them top color and bottom color, and let's set their values. You can see the ones I've used in the bottom part of the screen. Now let's add a lerp node that will interpolate the two colors and connect the two parameters to its inputs. Previewing the lerp, we can see that we need something to drive the alpha input of the lerp, because using just a number will result in the lerp node mixing the two colors together, but that's not what we want. We need a series of values for the alpha, so I've created a gradient texture that gives a transition similar to the one seen in Valorant. You can get the texture for free or donate whatever you want on Gumroad to support the channel. The link is in the description of this video. I've imported the texture into the engine and dragged it into the material graph. I could have used it as it was, but the gradient of the chaos grenade is not centered. In fact, the blue part is bigger than the purple one, so I've scaled the gradient in the material. To do that, let's add a texture coordinate node and connect it to the UV input of the gradient. Then, in the text coord, we can change the V tiling to stretch or compress the vertical coordinates. In my case, I went for a value of 0.75 to push down the black area of the gradient. That is the one addressed by the B input of the lerp node. Now we can connect the texture sample to the lerp alpha, and we can see how it affects the color of our material. Okay, now let's see how we can manipulate the geometry of our mesh using the Vertex Shader. But what is a Vertex Shader? As its name implies, this type of shader operates on the vertices of a mesh before it is rendered. It manipulates the attributes of the vertices, such as their position, color, and texture coordinates. You might wonder what's the difference between animating a part of a mesh and using a Vertex Shader. And the reason why you should prefer the latter is because the Vertex Shader operates directly on the GPU, making operations really optimized. Furthermore, its behavior could be dynamic and way more flexible than working with animations, because you could use parameters to instruct the engine to animate the vertices differently if needed, while using an animation would require more time to go back and change it. All of this is linked to the reason why, as stated before, we need a mesh that has the UVs of each triangle collapsed to one point. In this way, the Vertex Shader will operate on the position of that UV point, moving the whole triangle without deforming it. For the sake of clarity, this is what happens if you don't collapse the UV vertices. As you can see, the material is still manipulating the position of the triangles, but they are being deformed because the shader is moving each vertex separately. Back in our material, to feed the Vertex Shader, we need to connect something to the world position offset of the material. We are going to use a noise to drive the vertex movement. It's worth noting that, if you prefer, you can use a texture, but I wanted to experiment with the noise node, so I'm going to show you how to use it. First, let's add a noise node in the graph and enable its preview. Here we have a list of different ways to generate the noise, but in our case we don't need anything complex, so we can use a fast gradient, that's the lightest option in terms of performance. For the same reason, we are going to turn off turbulence and lower down the levels to 1. Set the output min to -0.1 and the output max to 0.15. The negative value of the output mean will make the vertices move inwards from their original position on the surface. Finally, we also want to scale it quite a lot, otherwise its influence won't be that evident, and you can set it to something like 14 or 15. Now we need to make this noise move, so let's add a panner node in the graph. If we try to connect the output of the panner to the world position input of the noise, we will get an error, and that's because the panner outputs a vector 2, but the noise needs a vector 3. So we are going to break the panner output using the breakout float 2 components node. Now we can add a make float 3 node and connect the R and G to the X and Y inputs, leaving the Z alone. What we have done is basically create a vector that moves along a plane, because one axis is 0. Connect the make float 3 output to the noise and check the preview. Now we got our moving noise. If you can barely see it, try to turn off automatic exposure in the viewport. The option is available when clicking on the view mode icon. Okay, we have a moving noise, but we need a way to sample the mesh. And to do that, we are going to use the absolute world position node. If we multiply its output with the noise and connect the result to the world position offset pin of the material, we can see in the preview that we are actually displacing the vertices. But if you apply the material to the mesh, we will see that something is wrong. And that's because the position we are sampling is absolute and relative to the world origin. So if we move the mesh, we will see the material behaving differently. But that's wrong, because we need it to behave in the same way independently from the mesh position. So to fix this, let's go back to the material editor and right-click and write transform. There will be two results. Be sure to select the transform position node and not the transform node. In the options, select absolute world space for the source and local space for the destination. Then insert the node before the multiply. In the preview you won't notice any change, but applying the material and going back to the level viewport, you'll see the difference. Now the Vertex Shader is using the local coordinates of the vertices, displacing them as we want, and the effect doesn't change if we move the mesh. The material is almost finished. The last thing we need to do is to give a different color to the sides of the triangles. This may seem an easy thing to do, but it actually requires some vector math, so bear with me. Since each triangle UV is collapsed to one point, there is no direct way to tell the engine where the sides of the triangles are, but we can use a vector operation called the dot product. Without dwelling into long explanations, what's important about this operation is that the result of the dot product of two perpendicular vectors is 0. So if the angle between two vectors is 90 degrees, the dot product will be 0. We can use this property to identify which pixels lie on the sides of the extruded triangles, because if the pixel position vector is 90 degrees to the corresponding face normal vector, it means that the pixel is on the side. In all other cases, the position vector will be almost parallel to the face normal vector. To do this comparison on all pixels, we can use the absolute world position and transform position nodes used before, and we also need the vertex normal node. Let's also add the dot product node and connect the vertex normal to the B input. Before connecting the position vector to the A input, we need to normalize the vector first, by using a normalized node. This is necessary because we only care about the direction of the vector and not its magnitude. Now we can connect the normalized output to the dot product. Let's create a vector tree for the triangle side color and convert it to a parameter. I called it side color and set it to the value shown at the bottom of the screen. The final bit in our material graph is the if node. We are going to use it to check the result of the dot product and set the color accordingly. The A input should receive the output of the dot product node and the B input is 0. So when A is 0, meaning that the two vectors are at 90 degrees, we know it's a side, so the color should be the side color. In all other cases, the color should be the gradient we created before. Now select the if node and adjust the threshold of the comparison by increasing it to 0.1. This is needed because the position vector of the pixel and the side face normal are not exactly at 90 degrees since the sphere is broken into multiple pieces. Finally, connect the output of the if node to the emissive color of the material and save it. Going back in the level viewport, we can see now that we have a gradient over the surface of the sphere and a different colors for the sides of the animated triangles. In the initial video, you surely noticed the greenish energy blasts coming out of the grenade. In the game, they are probably being spawned from a particle emitter, and I'm going to show you how to recreate something like that in a future video. So be sure to subscribe to the channel to not miss it. When it will be available, I'll put its link in the description of this video too. So that's all for today, guys. I hope you enjoyed this video and found it helpful. Remember that if you want to take your support to the next level, you can check out my Patreon page in the video description. Thank you so much for watching, and I'll see you in the next one. Until then, keep on creating and cheers!